When you look up at the night sky, you're seeing the past. Not metaphorically, but literally. The light reaching your eyes left those distant stars years ago, sometimes thousands of years ago. The farther away something is, the older the light we receive from it becomes. This simple fact transforms every telescope into a time machine, not in the science fiction sense of physical travel, but in observation. When astronomers point their instruments toward distant galaxies, they're not seeing those galaxies as they are now. They're seeing them as they were when the universe itself was younger. The James Webb Space Telescope operates on this principle, but pushes it further than any instrument before it. It looks so far into space that it sees galaxies as they existed when the universe was barely recognizable, when cosmic structures were just beginning to form, when the first light was spreading through what had been darkness. Understanding what Webb has shown us requires understanding light itself, how it travels, how it changes during its journey, and why looking far away means looking far back in time. The journey of light through space. Light moves quickly. In vacuum, it travels at just under 300,000 kilometers per second. Nothing moves faster. This speed, while enormous by human standards, becomes almost poetically slow when measured against cosmic distances. The nearest star beyond our sun lies just over 4 light-years away. This means the light we see from it tonight began its journey over 4 years ago. We're seeing that star not as it is, but as it was. If something dramatic happened to that star yesterday, we won't know for 4 more years. This delay grows with distance. Light from the Andromeda galaxy, our nearest large galactic neighbor, travels for roughly 2.5 million years before reaching Earth. When you see Andromeda in the night sky, you're seeing it as it appeared when our early human ancestors were just beginning to walk upright on the African plains. For more distant objects, these time scales become almost incomprehensible. Light from galaxies billions of light-years away has been traveling since before Earth existed, before our sun formed, before many of the stars we see in our own galaxy were born. But something else happens to light during these enormous journeys. The universe itself is not static. Space is expanding, growing larger with each passing moment. And as space expands, it stretches the light waves traveling through it. Redshift and the stretching of light. Imagine holding both ends of a spring. If you pull your hands apart, the spring stretches. The coils become farther apart from each other. Something similar happens to light waves as they travel through expanding space. Light behaves as a wave, with peaks and troughs following each other in regular patterns. The distance between these peaks is the wavelength. Different wavelengths correspond to different colors of light. Blue light has short wavelengths. Red light has longer wavelengths. Infrared radiation, which our eyes cannot see, has even longer wavelengths. As light travels through expanding space, the expansion stretches the wavelengths. Blue light becomes green. Green becomes yellow. Yellow becomes red. Red becomes infrared. The light shifts toward the red end of the spectrum, which is why astronomers call this effect redshift. The amount of stretching depends on distance. Light that travels farther gets stretched more. By measuring how much light has been redshifted, astronomers can calculate how far away the source is and how long the light has been traveling. For nearby galaxies, the redshift is small. The light hasn't changed much. But for the most distant galaxies Webb observes, the redshift is enormous. Light that left those galaxies as ultraviolet radiation, too blue for human eyes to see, arrives at the telescope as infrared radiation, too red for human eyes to perceive. This is why Webb was designed to see in infrared. The most distant objects in the universe, the ones from the earliest times, have had their light stretched so completely that they're invisible to telescopes that only observe visible light. The Hubble Space Telescope, despite its remarkable capabilities, couldn't see many of these ancient galaxies because their light had shifted beyond its detection range. Webb's instruments capture wavelengths from visible red light through mid-infrared, covering a range that allows it to see galaxies at almost any distance, including those from the universe's first billion years of existence. The limits of observation. There are theoretical limits to how far back in time we can see. These limits aren't set by technology, but by the nature of the universe itself. The universe began, according to our best understanding, approximately 13.8 billion years ago in an event we call the Big Bang. This wasn't an explosion in space, but rather the beginning of space itself. Time, as we understand it, began then as well. For roughly the first few 100,000 years after the Big Bang, the universe was opaque. It was filled with plasma so hot and dense that light couldn't travel freely through it. Photons would bounce off charged particles constantly, unable to move in straight lines. It was like trying to see through fog so thick that nothing beyond it is visible. Eventually, the universe cooled enough for atoms to form. This process, called recombination, happened about 380,000 years after the Big Bang. Once atoms existed, photons could finally travel freely through space. The universe became transparent. The light from that moment, the cosmic microwave background, fills the entire sky. It's been traveling through space ever since, and we can detect it today. But we cannot see anything from before that moment. The earlier universe is fundamentally invisible to direct observation because light couldn't travel through it. The first stars and galaxies didn't form immediately after recombination. They took time to develop. Current theories suggest the first stars ignited somewhere between 150 and 300 million years after the Big Bang. Before that, there were no stars to see, no galaxies. Just hydrogen and helium gas slowly clumping together under gravity's patient pull. Webb is approaching this observational horizon. The most distant galaxies it has found existed around 280 million years after the Big Bang. We're seeing structures from very near the beginning of cosmic illumination, when the universe's first lights were just turning on. Webb's design and capabilities. The James Webb Space Telescope was built specifically for this kind of observation. Every aspect of its design serves the purpose of seeing faint, distant, ancient objects. The telescope sits about 1.5 million kilometers from Earth, at a location called Lagrange Point 2. This position keeps Webb in permanent shadow from both the Earth and the Sun. This positioning is critical because the telescope must be kept extremely cold. Infrared radiation is heat radiation. Everything warm emits infrared light. If Webb's instruments were warm, they would glow brightly in infrared, drowning out the faint signals from distant galaxies. To prevent this, the telescope operates at temperatures around -233 degrees Celsius. That's colder than the surface of Pluto, colder than almost anywhere naturally occurring in our solar system. A massive sun shield, roughly the size of a tennis court when deployed, protects the telescope from solar radiation. The shield has 5 layers, each one helping to block heat and keep the instruments cold. The temperature difference between the sun-facing side and the cold side is enormous. Several hundred degrees Celsius of protection. The primary mirror is 6.5 meters across, much larger than Hubble's 2.4-meter mirror. This size difference is significant. Larger mirrors collect more light, allowing fainter objects to become visible. Webb's mirror has about 6 times the collecting area of Hubble's, meaning it can see considerably fainter sources. The mirror is made of 18 hexagonal segments, each coated with a thin layer of gold. Gold was chosen because it reflects infrared light particularly well. Each segment can be adjusted independently by tiny motors, allowing the entire mirror to focus with remarkable precision. Behind the mirror sit the instruments that actually detect the light. Webb carries multiple cameras and spectrographs, each designed for different wavelength ranges and different types of observations. Some instruments capture images. Others split light into its component wavelengths, creating detailed spectra that reveal what distant objects are made of. When Webb observes a patch of sky, it typically stares at it for hours or even days. The longer it looks, the more photons it collects from faint sources. Galaxies too dim to see in short exposures gradually appear as the observation continues. Light that left those galaxies billions of years ago trickles in, photon by photon, until enough have accumulated to form an image. The observable universe and its scale. The universe we can observe is finite, not because the universe itself ends, but because light from more distant regions hasn't had time to reach us yet. If the universe is 13.8 billion years old, you might expect we could see objects up to 13.8 billion light-years away. But the reality is more complex. The universe has been expanding during the entire time that light has been traveling toward us. Space itself has grown larger. An object whose light has been traveling for 13 billion years is no longer where it was when it emitted that light. The expansion of space has carried it much farther away. When we calculate the current distance to the most distant observable objects, accounting for this expansion, we find they're now about 46 billion light-years away in all directions. This creates an observable universe with a diameter of approximately 93 billion light-years. Everything within this sphere is, in principle, observable if we have instruments sensitive enough to detect it. Everything beyond this sphere is currently unobservable because light from there hasn't reached us yet. The observable universe expands with time. Each moment, light from slightly more distant regions reaches us. The boundary moves outward. But this expansion is slower than you might expect because the universe's own expansion is accelerating. Regions that are far enough away are receding from us faster than light can travel toward us. We will never receive light from those regions, regardless of how long we wait. Within the observable universe, the number of galaxies is staggering. Recent estimates suggest somewhere around 2 trillion galaxies exist within the volume we can potentially observe. Each one is a collection of stars, gas, dust, and dark matter, bound together by gravity. Each one has its own history of formation and evolution. 2 trillion is a number difficult to grasp intuitively. If you tried to count to 2 trillion at a rate of 1 number per second, working continuously without rest, it would take over 63,000 years. If every person currently alive on Earth took responsibility for learning about just one galaxy, we'd need to visit nearly 300 galaxies each. And these are just the galaxies we can potentially observe. The universe almost certainly extends far beyond the observable sphere. How much farther is unknown. It might extend infinitely, or it might curve back on itself in ways we can't easily visualize. We can only study the portion accessible to our observations. The first deep field, a grain of sand against the sky. One of Webb's earliest images targeted a galaxy cluster called SMACS 0723. The telescope stared at this region for 12.5 hours, collecting light continuously. The area of sky covered by this image is extraordinarily small. If you held a grain of sand at arm's length toward the sky, that grain would cover approximately the same angle. From our perspective, this is an almost invisibly tiny slice of the cosmos. Yet within this minute region, Webb detected thousands of galaxies. Nearly 10,000 distinct galaxies appear in that single image. Each one is a complete stellar system, potentially containing billions or trillions of stars. The galaxies appear at various distances. Some are relatively nearby, only a few billion light-years away. Their light shows them as they appeared when the universe was already quite mature, when Earth was already billions of years old. These galaxies often show familiar structures, spiral arms, central bulges, regular shapes. Others are much more distant. Their light left them when the universe was less than 1 billion years old. These galaxies appear smaller and more irregular. Many look like they're still in the process of forming, assembling themselves from smaller pieces. The galaxy cluster itself, SMACS 0723, lies about 4 billion light-years from Earth. It contains hundreds of large galaxies, all bound together by their mutual gravitational attraction. The combined mass of all these galaxies, plus the dark matter surrounding them, warps the fabric of space-time in the region. This warping creates an effect called gravitational lensing. Light from galaxies far behind the cluster passes through the curved space-time around the cluster. The curving bends the light paths, changing the apparent position and shape of background galaxies. Some galaxies appear stretched into long arcs. Others appear multiple times in different locations. Some are magnified, becoming brighter and easier to see than they would be without the lensing effect. Gravitational lensing acts as a natural telescope, allowing Webb to see galaxies that would otherwise be too faint to detect. The cluster's gravity does work that no human-made instrument could accomplish, bringing distant galaxies into view. The diversity visible in this single image is remarkable. Young galaxies actively forming stars, with blue and ultraviolet light indicating hot, newly born stellar populations. Old galaxies where star formation has ceased, appearing reddish because only cool, elderly stars remain. Galaxies in the process of merging, their shapes distorted by gravitational interactions. Isolated galaxies that have evolved quietly over billions of years. Each galaxy represents an independent history. Different initial conditions, different encounters with neighboring galaxies, different rates of star formation, different experiences with the universal environment. No two paths through cosmic time are identical. When you consider that this extraordinary diversity exists in a region the size of a grain of sand at arm's length, the implications become overwhelming. The entire sky contains over 40,000 square degrees. If every comparable region contains similar numbers of galaxies, the total becomes incomprehensible. 2 trillion galaxies, each one a cosmos unto itself. Understanding galaxy formation, galaxies don't form instantly. They grow gradually over hundreds of millions or billions of years through processes that astronomers are still working to fully understand. The early universe, just after recombination, when atoms first formed, was remarkably uniform. The temperature and density of matter were nearly the same everywhere, but not perfectly uniform. Tiny variations existed, regions where matter was slightly denser than average, and regions where it was slightly less dense. These variations, though small, were enough. Gravity amplifies density differences. Regions that are slightly denser have slightly stronger gravitational pull. They attract more matter toward themselves. As they accumulate more matter, their gravitational pull grows stronger still, attracting even more matter. The process feeds on itself. Dark matter played a crucial role in this process. Dark matter, which doesn't interact with light or ordinary matter except through gravity, makes up roughly 85% of all matter in the universe. It started clumping together first, forming halos of increased density. These halos then attracted ordinary matter, hydrogen and helium gas. As gas fell into dark matter halos, it accumulated in the gravitational wells. Eventually, enough gas collected that gravitational collapse could begin. Dense regions within the gas collapsed inward, pressure and temperature rising as matter compressed. When temperatures reached tens of millions of degrees, nuclear fusion ignited. Stars were born. The first generation of stars were different from modern stars. They formed from primordial gas, pure hydrogen and helium, with essentially no heavier elements. This composition affected their structure. Without heavier elements to help radiate away energy, the gas clouds couldn't cool as efficiently. They couldn't fragment into small pieces. The result was stars that were likely quite massive, perhaps dozens or hundreds of times heavier than our sun. These massive stars burned hot and bright, but lived briefly. The most massive ones exhausted their nuclear fuel in just a few million years, then exploded as supernovae. These explosions were transformative events. They scattered the first heavier elements into the surrounding space: carbon, oxygen, nitrogen, silicon, iron, and others. These elements had been forged inside the stars through nuclear fusion. The next generation of stars formed from gas that had been enriched by these earlier explosions. They contained small amounts of heavier elements. This changed their properties. They could cool more efficiently, fragment into smaller pieces, form in a wider range of masses. Star formation became more diverse. Over time, more and more stars formed. The proto-galaxies grew larger, accumulated more mass, underwent occasional mergers with neighboring systems. The process wasn't smooth or uniform. It was chaotic, driven by random encounters and the complex interplay of gravity, gas dynamics, and stellar evolution. Modern galaxies are the products of billions of years of this gradual assembly. They contain stars of many different ages, from ancient stars that formed in the early universe to young stars being born today. They contain gas that will form future generations of stars. They contain the remnants of dead stars, white dwarfs, neutron stars, black holes, and they're embedded in massive halos of dark matter that extends far beyond the visible stellar components. What Webb has revealed: when Webb began observations, astronomers had specific expectations based on theoretical models. These models predicted how many galaxies should exist at different distances, how bright they should be, how large they should be. The observations have challenged many of these predictions. Webb has found more bright galaxies in the early universe than models predicted. Galaxies that existed just a few 100 million years after the Big Bang are more numerous and more luminous than expected. Some are actively forming stars at rates that seem implausibly high. Others appear more mature and developed than their young ages would suggest. In particular, Webb has discovered galaxies that seem to have assembled very quickly. Galaxies that contain billions of solar masses worth of stars already existed when the universe was less than 500 million years old. Building this much stellar mass in such a short time requires star formation rates significantly higher than what we see in galaxies today. Why were these early Galaxies so efficient at forming stars? Several possibilities exist. Perhaps gas was denser in the early universe, allowing more rapid collapse. Perhaps the first stars were more massive on average, producing more light per star. Perhaps the conditions for star formation were simply more favorable, with fewer processes disrupting the collapse of gas clouds. Another surprise involves galaxy structure. Theoretical models generally predicted that early galaxies would be small and irregular, gradually growing larger and more organized over time. Webb has found that many early galaxies already show signs of structure: rotating disks, central concentrations of stars, organized patterns rather than pure chaos. This doesn't mean the models are entirely wrong, but it suggests they're incomplete. Some physical processes that were thought to be unimportant in the early universe might actually be quite significant. Or perhaps the initial conditions, the density variations seeded by the Big Bang itself, were stronger than we realized. The discoveries have particular implications for understanding how quickly structure could form. If galaxies were assembling faster than expected, if they were becoming brighter and more massive earlier than predicted, then other aspects of cosmic evolution might also have proceeded more rapidly. The timeline for various cosmic milestones may need revision. Black holes in the early universe. Among the most puzzling discoveries are black holes. Specifically, supermassive black holes found in galaxies that existed when the universe was very young. Black holes form when massive stars collapse at the end of their lives. A star many times heavier than our Sun exhausts its nuclear fuel, and its core implodes under its own gravity. If the star is heavy enough, the collapse continues until a black hole forms. These stellar mass black holes typically weigh between a few and a few dozen times the mass of the Sun. Supermassive black holes are vastly larger. They weigh millions or billions of solar masses. Nearly every large galaxy contains one at its center. Our own galaxy, the Milky Way, hosts a supermassive black hole weighing about 4 million times the Sun's mass. How do supermassive black holes grow so large? The standard explanation involves gradual growth over cosmic time. A stellar mass black hole forms first, then slowly accumulates more mass by pulling in surrounding gas. Each bit of gas that falls in adds to the black hole's mass. Over hundreds of millions or billions of years, the black hole grows from stellar mass to supermassive. This process has a natural speed limit. When matter falls toward a black hole, it doesn't fall straight in. It forms a swirling disk around the black hole, called an accretion disk. Friction in this disk heats the matter to extremely high temperatures, millions of degrees. Hot matter emits intense radiation, including ultraviolet light and X-rays. This radiation creates pressure that pushes outward. If too much matter tries to fall in at once, the radiation pressure becomes strong enough to blow away the incoming material. The black hole essentially chokes on its food, unable to consume matter faster than a certain rate. This maximum rate is called the Eddington limit. At the Eddington limit, a black hole can roughly double its mass every few tens of millions of years. Starting from a stellar mass black hole weighing 50 solar masses, reaching 1 million solar masses takes about 700 million years of continuous feeding at maximum rate. Reaching 1 billion solar masses takes closer to 1 billion years. The problem is that Webb has found supermassive black holes in galaxies that existed less than 1 billion years after the Big Bang. Some existed when the universe was only 500 million years old. The timeline seems insufficient for them to have grown from stellar mass seeds through normal accretion. This has led to several theoretical proposals. Perhaps black holes didn't start from stellar mass seeds. Perhaps they formed directly from collapsing gas clouds, beginning their lives already weighing thousands or tens of thousands of solar masses. This head start would dramatically reduce the time needed to grow to supermassive scales. Alternatively, perhaps black holes could feed faster than the Eddington limit under certain conditions. If matter fell in from all directions simultaneously, overwhelming the outward radiation pressure through sheer volume, the growth rate might exceed normal expectations. This kind of super Eddington accretion has actually been observed in at least one case, though it's thought to be rare and short-lived. Or perhaps both factors contributed. Heavy seed black holes forming early, then experiencing episodes of rapid feeding, could reach supermassive scales in the available time. Whatever the explanation, the existence of these early supermassive black holes tells us something important about the young universe. Conditions must have allowed rapid black hole growth, faster than what typically occurs in the modern cosmos. Understanding exactly how this happened remains an active area of research. The cosmic dawn and reionization. The period when the first stars formed is called the cosmic dawn. Before this time, the universe was dark. After it, light began to fill the cosmos. This wasn't a sudden transition. The first stars didn't all form simultaneously. They appeared gradually in scattered locations over a period of perhaps 100 million years or more. Early on, most of space remained dark. Small regions around the first stars glowed, but vast volumes between them were still filled with neutral hydrogen gas. The ultraviolet radiation from early stars had an important effect on this neutral hydrogen. Ultraviolet photons carry enough energy to ionize hydrogen atoms, stripping away their electrons. Each young, hot star emitted tremendous amounts of ultraviolet light, creating a bubble of ionized gas around itself. At first, these bubbles were isolated. As more stars formed, more bubbles appeared. Eventually, the bubbles began to overlap, merging into larger ionized regions. This process, called reionization, gradually transformed the universe from a place filled with neutral hydrogen into one filled with ionized plasma. Reionization took time. It probably began around 200 million years after the Big Bang and wasn't complete until perhaps 500 or 600 million years after. The exact timeline is uncertain because it depends on how quickly stars formed and how much ultraviolet light they produced. Webb's observations of early galaxies help constrain this timeline. By measuring how many bright galaxies existed at different times, astronomers can estimate how much ultraviolet light was present. More bright galaxies means more ultraviolet radiation, means faster reionization. Current observations suggest the universe was largely reionized by about 400 to 500 million years after the Big Bang. The galaxies Webb has found seem capable of producing enough ultraviolet light to accomplish this, though the calculations are still being refined. Reionization had lasting effects on galaxy formation. Once the universe was ionized, gas in smaller gravitational wells couldn't easily collapse to form stars. The ionized gas had higher pressure, resisting compression. This suppressed star formation in low-mass halos, preventing the formation of very small galaxies. This explains why we don't see huge numbers of tiny dwarf galaxies in the modern universe, despite theoretical predictions that dark matter halos of all sizes should exist. The smallest halos do exist, but they remain dark. They contain gas that was ionized during reionization and never cooled enough to form stars. Only halos above a certain mass threshold retained enough gravitational pull to overcome the gas pressure and continue forming stars. The cosmic dawn and ionization represent a fundamental transition in cosmic history. Before, the universe was dark and simple. After, it was illuminated and complex. This transition happened quickly on cosmic timescales, over just a few 100 million years out of the universe's 13.8 billion year existence. Gravitational lensing as a natural telescope. We've mentioned that massive objects bend light through gravitational lensing. This effect deserves deeper exploration because it's crucial to Webb's most distant observations. Einstein's general relativity describes gravity not as a force, but as the curvature of spacetime. Mass curves the fabric of spacetime around itself. Objects moving through this curved spacetime follow curved paths. This includes light. When light from a distant galaxy passes near a massive object like another galaxy or a galaxy cluster, the light's path bends. The massive object acts like a lens, focusing the light. From our perspective, this can have several effects. First, the image of the distant galaxy can appear in multiple locations. Light takes different paths around the lensing mass, arriving at our telescopes from several directions. Each path creates a separate image. Sometimes we see two images, sometimes four, sometimes arcs or rings. Second, the galaxy's image gets distorted. It might appear stretched into a long arc, or smeared into a partial ring around the lensing object. The shape we see is not the galaxy's true shape, but a distorted version created by the bending of light paths. Third, the galaxy's light is magnified. The lensing effect concentrates light that would otherwise spread out over a larger area of sky. This makes the background galaxy appear brighter than it would without the lensing. This magnification can be substantial, sometimes factors of 10 or 20 or even more. For astronomers, this magnification is enormously valuable. Galaxies that would be too faint to detect even with Webb become visible when magnified by gravitational lensing. The universe provides us with natural telescopes, scattered in the form of galaxy clusters, that amplify distant light and bring remote objects into view. Webb has targeted many known lensing clusters precisely for this reason. By observing through these natural lenses, the telescope can see galaxies it couldn't detect through direct observation. The most distant galaxies discovered so far have often been found in fields containing strong gravitational lenses. The challenge with lensed images is that they're distorted. To understand the true properties of the background galaxy, astronomers must model the lensing effect and reverse it. This requires knowing the mass distribution of the lensing object, which isn't always straightforward. The lensing cluster might contain hundreds of individual galaxies, each contributing to the overall gravitational field. Dark matter, which outweighs visible matter by about 5 to 1, also contributes significantly but can't be directly seen. By carefully analyzing multiple lensed images of background galaxies, astronomers can map out the mass distribution of the lensing cluster. This includes the distribution of dark matter. The resulting maps show that dark matter typically forms a smooth halo centered on the cluster, with dense concentrations at the core and more diffuse material extending far beyond the visible galaxies. Sometimes, rare alignments create particularly strong lensing effects. If multiple massive structures line up along the same line of sight, their lensing effects compound. These cosmic coincidences can create magnifications of 100 times or more, allowing glimpses of extraordinarily faint and distant objects. Einstein predicted gravitational lensing as a consequence of general relativity, but thought it would likely never be observed because the effects would be too small. He was proven wrong. The first gravitational lens was discovered in 1979, and since then hundreds have been found. Modern surveys identify lensing effects routinely. The effect Einstein thought impractical has become an essential tool for observational astronomy. The puzzle of early galaxy brightness. Let's return to a question raised earlier. Why are early galaxies brighter than expected? Theoretical models of galaxy formation are sophisticated. They incorporate our understanding of gravity, gas dynamics, star formation, stellar evolution, and the feedback processes by which stars affect their surroundings. These models are run on supercomputers, simulating the evolution of regions of the universe from shortly after the Big Bang to the present day. The simulations predict how many galaxies should form, when they should form, how massive they should be, and how bright they should appear. Before Webb, these predictions matched observations reasonably well. The number and brightness of galaxies that Hubble detected at various distances aligned with theoretical expectations. Webb's observations have revealed discrepancies. There are more bright galaxies in the early universe than simulations predicted. Some galaxies appear at least 10 times brighter than they should be, based on their ages and expected stellar populations. Several possible explanations exist, and the truth might involve a combination of factors. One possibility involves the stars themselves. If early galaxies formed a higher proportion of massive stars than modern galaxies do, they would be brighter. Massive stars are far more luminous than small stars. A star 100 times the Sun's mass can be 1,000,000 times brighter. If the stellar population was skewed toward these luminous giants, the total light output would increase dramatically. Why might early galaxies favor massive stars? The composition of gas matters. The first stars formed from pristine hydrogen and helium. Modern stars form from gas enriched with heavier elements. These heavier elements help gas clouds cool and fragment into smaller pieces. Without them, clouds might collapse into fewer, more massive stars. Another possibility involves exotic objects called supermassive stars. These hypothetical stars would be hundreds or thousands of times heavier than ordinary massive stars. They would shine with incredible intensity, but live extremely brief lives, perhaps only a few million years before exploding or collapsing into black holes. If even a small fraction of a galaxy's stellar population consisted of supermassive stars, they could dominate the total light output. However, supermassive stars remain theoretical. None have been definitively observed. Whether they actually existed in the early universe is uncertain. Black holes might also contribute. Active supermassive black holes, surrounded by bright accretion disks, emit enormous amounts of light. If early galaxies contained more actively feeding black holes than expected, this additional light source could boost the overall brightness. Some of the brightest early galaxies do show signs of black hole activity, though not all. Star formation efficiency could play a role. Perhaps early galaxies converted gas into stars more efficiently than modern galaxies. Modern star formation is a messy process. Much of the gas in a star-forming region doesn't end up in stars. It gets heated by stellar radiation, blown away by stellar winds, or disrupted by supernova explosions. If these disruptive processes were weaker in early galaxies, more gas would successfully form stars, increasing the total stellar population and thus the brightness. The presence of dust could complicate brightness measurements. Dust absorbs ultraviolet and visible light, then re-emits it as infrared radiation. This changes the apparent brightness in different wavelengths. If early galaxies contained more dust than expected, or if the dust distribution was different from what models assume, it could affect brightness estimates. Finally, the cosmological parameters themselves might need adjustment. The models use specific values for the density of dark matter, the strength of dark energy, and the amplitude of initial density variations. If these values are slightly different from what we've assumed, the predictions would change. However, these parameters are constrained by multiple independent observations, so there's limited room for adjustment without creating conflicts with other data. Resolving this puzzle requires more observations and better theoretical models. Webb continues to survey early galaxies, building up larger samples that will allow more robust statistical analysis. Theorists are revisiting their simulations, exploring different assumptions about star formation, feedback processes, and initial conditions. Gradually, observation and theory will converge on an explanation. The expansion of space and the Hubble tension. We've discussed how space expands, stretching light waves and creating redshift. But how fast is space expanding? This question has a surprisingly contentious answer. The expansion rate is quantified by the Hubble constant. Despite its name, this constant changes over cosmic time, but at any given moment, it has a specific value. That value tells us how quickly the universe is growing. Specifically, the Hubble constant describes the relationship between distance and recession velocity. A galaxy twice as far away recedes twice as fast. 3 times as far away, 3 times as fast. The Hubble constant is the proportionality factor linking these quantities. There are 2 main methods for measuring the Hubble constant, and they give different answers. The first method uses observations of the cosmic microwave background, the faint glow left over from recombination when the universe became transparent. This radiation fills the entire sky and carries information about the universe as it existed 380,000 years after the Big Bang. By analyzing tiny temperature variations in this radiation, astronomers can determine the expansion rate at that time. They then use theoretical models to project forward to the present day, calculating what the Hubble constant should be now. This method gives a value of approximately 67 kilometers per second per megaparsec. A megaparsec is roughly 3.3 million light-years. So this measurement says that for every megaparsec of distance, galaxies are receding about 67 kilometers per second faster. The second method uses observations of nearby objects, stars and galaxies whose distances can be measured directly. Certain types of stars, called Cepheid variables, pulsate regularly, and their pulsation periods relate directly to their intrinsic brightness. By measuring the period and the apparent brightness, astronomers can calculate distance. Type Io supernovae also serve as distance markers because they all have similar intrinsic brightness. By measuring distances to galaxies and comparing those distances to the galaxy's recession velocities, astronomers calculate the Hubble constant directly from local observations. This method gives a value of approximately 73 kilometers per second per megaparsec. The discrepancy, about 6 kilometers per second per megaparsec, might seem small. But both measurements are quite precise, with uncertainties of only about 1 or 2 in their values. The difference is statistically significant. The 2 methods genuinely seem to be giving different answers. This is called the Hubble tension, and it's one of modern cosmology's major puzzles. Webb has contributed to this puzzle by confirming the local measurements. There was concern that perhaps the Hubble Space Telescope's observations contained systematic errors. Maybe the distance measurements to Cepheid variables were slightly wrong. Webb can observe the same Cepheid variables with better sensitivity and precision. It has confirmed Hubble's measurements. The local expansion rate really does seem to be about 73. So why the discrepancy? several possibilities exist. Perhaps our understanding of the early universe is incomplete. If conditions 380,000 years after the Big Bang were slightly different from what we assume, the projection to present-day expansion rate would change. This might require new physics, some property of matter or energy that we haven't accounted for. Perhaps dark energy behaves differently than we think. Dark energy is the mysterious component driving the universe's accelerating expansion. We don't know what it is. We only know it exists because we observe its effects. If dark energy's strength has changed over cosmic time, rather than remaining constant, this could potentially resolve the tension. Perhaps there's an additional, undiscovered component to the universe, something that affects expansion, but that we haven't detected yet. This would require new physics beyond our current cosmological model. Or perhaps one of the measurement methods has a subtle systematic error that hasn't been identified. Despite extensive checking, measurements are complex and rely on many assumptions. An unrecognized error in either method could create an apparent discrepancy. The tension remains unresolved. Both measurement methods have been scrutinized extensively. Both have been refined and improved. The discrepancy persists. Resolving it may require breakthrough observations or theoretical insights that we don't yet have. The search for population 3. Stars are classified into populations based on their chemical composition. This classification system is slightly counterintuitive. Population Y stars, like our Sun, are relatively rich in heavy elements. They're the youngest population. Population 2 stars contain fewer heavy elements. They're older, having formed from gas that hadn't been as enriched by previous stellar generations. Population 3 stars would be the first stars, formed from the primordial gas that existed after the Big Bang. Pure hydrogen and helium, with essentially no heavier elements at all. These stars have never been definitively observed, despite extensive searches. Why do we think population 3 stars existed? Because every star we observe today contains at least trace amounts of heavy elements. Those elements had to come from somewhere. They couldn't have existed initially because the Big Bang produced only hydrogen, helium, and tiny amounts of lithium. Heavier elements form inside stars through nuclear fusion and get scattered into space when massive stars explode as supernovae. For there to be heavier elements in second-generation stars, first-generation stars must have created them. Population 3 stars, by definition, would be those first stars, the ones that forged the initial heavy elements. What would population 3 stars look like? Theoretical models suggest they would likely be quite massive, perhaps 50 to several hundred times the Sun's mass. The lack of heavy elements would affect how gas clouds cooled and fragmented. Without efficient cooling, clouds couldn't break into small pieces. They'd collapse into larger, more massive objects. Massive stars are hot and luminous. They emit huge amounts of ultraviolet radiation. They also live briefly, burning through their nuclear fuel in just a few million years before exploding. The most massive ones might skip the supernova phase entirely, collapsing directly into black holes. Finding population 3 stars is challenging because they existed so long ago. Any that still survive would be in the most distant galaxies, visible only as they appeared in the universe's first few 100 million years. Their light would be faint and highly redshifted. More likely, we won't find individual population 3 stars, but rather galaxies that contain them. If a galaxy shows a spectrum with extremely low heavy element content, far lower than any galaxy observed before, that might indicate the stars are predominantly population 3. Webb has found candidate galaxies, objects whose spectra show very little metal content, primarily just hydrogen and helium emission. These might be galaxies where population 3 stars are still a significant fraction of the stellar population. However, confirming this requires more detailed observations. Detecting individual population 3 stars would require even more sensitivity than Webb currently provides. These stars would be extraordinarily faint, both because of their distance and because a single star emits far less light than an entire galaxy. Future telescopes, with larger mirrors and more sensitive instruments, might eventually resolve individual stars in the earliest galaxies. The importance of finding population 3 stars goes beyond completing the stellar classification system. These stars were the universe's cosmic alchemists, transforming simple elements into complex ones. They created the first carbon, oxygen, nitrogen, silicon, iron, and all the other elements necessary for planets and life. They ionized the early universe. They seeded the formation of later stellar generations. Understanding these pioneers tells us how the universe transformed from simplicity to complexity. Timescales and cosmic evolution. It's worth pausing to consider timescales. The numbers involved in cosmic evolution are so large that they lose intuitive meaning. 13.8 billion years is difficult to comprehend. Perhaps some comparisons help. If the entire history of the universe were compressed into a single year, with the Big Bang occurring at midnight on January 1st, the first stars would ignite around January 7th or 8th. The universe would remain dominated by early star formation through most of January. Our Milky Way galaxy would form around February. Through spring, summer, and fall, galaxies would evolve, merge, and mature. The universe would gradually take on a structure similar to what we see today. Our solar system wouldn't form until early September. Earth wouldn't appear until a few days later. The first simple life on Earth would emerge in mid-September. But complex life, multicellular organisms, wouldn't appear until November. Dinosaurs would walk the Earth in mid-December. They'd go extinct on December 26th. Modern humans would appear at around 11:50 p.m. on December 31st. All of recorded human history would occupy the last few seconds before midnight. This perspective emphasizes how recent we are. The universe existed for over 9 billion years before our planet formed. It existed for over 13 billion years before anything resembling human civilization appeared. We're observing a cosmos that was already ancient before we arrived. Yet in another sense, we're quite fortunate in our timing. We live during an era when stars still form, when galaxies still evolve, when the universe is rich with structure and activity. This won't always be true. The universe's expansion is accelerating, driven by dark energy. Eventually, billions of years from now, expansion will carry distant galaxies beyond our observational horizon. They'll recede faster than light can travel toward us. The observable universe will gradually shrink, containing fewer and fewer galaxies. Star formation will continue for a long time, but not forever. Eventually, galaxies will exhaust their gas supplies. Stars will continue to form from remaining reserves, but the rate will decline. Tens or hundreds of billions of years from now, star formation will cease entirely. The universe will contain only long-lived stars and stellar remnants. White dwarfs, neutron stars, black holes. On even longer timescales, those remnants will fade. White dwarfs will cool to black dwarfs. Black holes will slowly evaporate through Hawking radiation. The universe will become increasingly dark and cold and empty. This distant future is unimaginably remote, not billions of years away, but trillions or quadrillions or even longer. We exist during the universe's luminous phase, when stars shine and galaxies gleam and structure fills the cosmos. This phase, while long by human standards, is relatively brief in the full arc of cosmic time. We're fortunate to be here when there's still so much light to observe. The nature of dark matter. Throughout this discussion, dark matter has appeared repeatedly. It's worth examining what we know and don't know about this mysterious substance. Dark matter is called dark because it doesn't interact with light. It doesn't emit, absorb, or scatter electromagnetic radiation. You can't see it with telescopes, regardless of what wavelength you observe in. Its presence is detected only through gravitational effects. Several lines of evidence demonstrate dark matter's existence. Galaxy rotation curves were one of the first clues. When astronomers measure how fast stars orbit in spiral galaxies, they find that stars in the outer regions move faster than they should if only visible matter were present. The gravitational pull of visible stars and gas isn't strong enough to keep these outer stars bound to the galaxy. Either they should fly off into space, or there must be additional unseen mass providing extra gravitational pull. Gravitational lensing provides another line of evidence. The amount of lensing produced by galaxy clusters can be measured by analyzing how background galaxies appear distorted. The lensing strength depends on total mass. When astronomers calculate the mass needed to produce the observed lensing, it's far greater than the mass of visible matter in the cluster. Additional unseen mass must be present. The cosmic microwave background offers yet another constraint. The detailed pattern of temperature variations in this ancient radiation depends on how much matter existed in the early universe and what properties it had. The observed pattern matches predictions only if dark matter exists in specific amounts with specific properties. Multiple independent measurements all point to the same conclusion. Dark matter exists. It outweighs ordinary matter by about 5 to 1. It doesn't interact with light or with ordinary matter except through gravity. It forms halos around galaxies and fills the space in galaxy clusters. It was crucial for structure formation, providing the gravitational wells that attracted ordinary matter and allowed galaxies to form. But what is it? This remains unknown. It's not ordinary matter that happens to be dark, like planets or black holes or cold gas clouds. Those are made of atoms, and we can account for all the atomic matter through multiple observations. Dark matter must be something else entirely. Leading candidates include exotic subatomic particles that haven't yet been detected in experiments. These particles would have been created in the early universe and would still be present today, but they'd interact so weakly with ordinary matter that they'd be extraordinarily difficult to detect. Numerous experiments have attempted to directly detect dark matter particles. So far, none have succeeded. This doesn't mean dark matter doesn't exist, only that it's even more elusive than expected. Perhaps the particles interact even more weakly than theorists thought. Perhaps we're looking in the wrong places or in the wrong ways. Alternative theories propose modifications to gravity rather than new particles. Maybe Einstein's general relativity isn't quite correct on galactic scales. Maybe gravity behaves differently than we think when dealing with very low accelerations or very large distances. Modified gravity theories can explain some dark matter evidence, but they struggle with other observations, particularly gravitational lensing and the cosmic microwave background pattern. The mainstream view remains that dark matter consists of new particles, but until those particles are detected directly, uncertainty remains. We know dark matter exists because we observe its gravitational effects. We know approximately how much exists and where it's distributed, but we don't know what it's made of. The role of dark energy. If dark matter is mysterious, dark energy is even more so. Dark energy makes up roughly 68% of the universe's total energy content, yet we understand essentially nothing about its nature. Dark energy was discovered through observations of distant supernovae in the late 1990s. Astronomers were measuring how the universe's expansion rate has changed over cosmic time. The expectation was that expansion should be slowing down. The mutual gravitational attraction of all matter in the universe should act as a brake, gradually decreasing the expansion rate. Instead, observations showed that expansion is accelerating. Distant supernovae appeared fainter than expected, indicating they're farther away than they should be if expansion were slowing. The universe is growing larger at an increasingly rapid rate. This acceleration requires some form of energy that creates a repulsive gravitational effect. This energy has been termed dark energy. The simplest model is that dark energy is a property of space itself, a sort of background energy density that remains constant even as space expands. This is sometimes called the cosmological constant. If space has an inherent energy density, then as space expands and more space comes into existence, the total amount of dark energy increases. This growing dark energy density drives ever faster expansion. The more space there is, the more dark energy there is, the faster expansion accelerates. The process feeds on itself. Why does dark energy cause repulsive gravity? In Einstein's general relativity, energy and pressure both contribute to gravity. Normal matter and dark matter have negligible pressure, so their gravity is purely attractive. But dark energy, in the cosmological constant model, has negative pressure. This negative pressure creates a repulsive gravitational effect that overcomes normal attraction. As the universe expands, the density of matter decreases. There's the same amount of matter, but it's spread over a larger volume, so the density drops. Dark matter density decreases similarly, but dark energy density stays constant. As time passes, dark energy becomes increasingly dominant. In the early universe, matter dominated. Its gravity was strong enough that it would have slowed expansion had dark energy not existed. But as the universe expanded and matter density dropped, dark energy gradually became more important. Eventually, a few billion years ago, dark energy density exceeded matter density. Expansion began to accelerate. This acceleration continues today and will continue indefinitely into the future. What is dark energy? We don't know. The cosmological constant model fits observations, but it doesn't explain why the constant has the value it does. Theoretical physics suggests the vacuum energy of space should be either zero or vastly larger than observed, not the intermediate value we actually measure. Alternative models propose that dark energy is not constant, but varies over time. Perhaps it's a field, similar to other fields in physics, that changes dynamically. This would be called quintessence. However, current observations suggest that if dark energy varies, it does so very slowly. Its properties have been essentially constant over the past several billion years. Some theories question whether dark energy exists at all. Perhaps general relativity needs modification on cosmological scales. Perhaps gravity behaves differently when dealing with the entire universe than when dealing with smaller structures. These modified gravity theories face challenges explaining all observations, but they remain actively studied alternatives. Dark energy's existence and properties affect the universe's ultimate fate. If dark energy remains constant, expansion will continue accelerating forever. The universe will grow increasingly cold, dark, and empty over trillions of years. If dark energy strengthens over time, expansion might eventually become so rapid that it tears apart galaxies, stars, planets, atoms themselves in a big rip. If dark energy weakens, expansion might eventually slow and perhaps reverse, leading to a big crunch. Current observations suggest the first scenario, eternal accelerating expansion, is most likely. But our understanding of dark energy is so limited that these long-term predictions remain quite uncertain. The cosmic web. On the largest scales, the universe has structure. Galaxies are not distributed randomly through space. They form patterns, clusters, filaments, walls, and voids. Galaxy clusters are regions where hundreds or thousands of galaxies congregate, held together by mutual gravity. We've discussed these as gravitational lenses, but clusters themselves are part of larger structures. Clusters connect to other clusters through filaments, elongated structures stretching across tens or hundreds of millions of light years. These filaments contain galaxies, gas, and dark matter. They're the largest coherent structures in the universe. Between filaments lie voids, vast regions containing relatively few galaxies. Voids can be hundreds of millions of light years across. They're not completely empty, but they contain far lower density than the cosmic average. This arrangement, filaments and voids creating a web-like pattern, is called the cosmic web. It's the universe's largest scale structure. The cosmic web originated from tiny density variations in the early universe. Regions that were slightly denser than average attracted more matter through gravity. As matter accumulated, these dense regions became denser still. Underdense regions lost matter to denser neighbors, becoming voids. Dark matter dominated this process. It started clumping first, forming a scaffolding. Ordinary matter, hydrogen and helium gas, followed the dark matter, falling into the gravitational wells. Where multiple dark matter filaments intersected, especially dense regions formed. These nodes in the cosmic web became sites of intense galaxy formation, eventually growing into galaxy clusters. The pattern is remarkably similar to other network structures, neural networks in brains, fungal mycelium in forests, urban transportation networks. They all show similar topologies, nodes connected by paths with empty spaces between. The underlying reason is mathematical. Network efficiency tends to create these patterns regardless of the specific physical processes involved. Webb's observations show that the cosmic web was already forming when the universe was quite young. Surveys of early galaxies reveal that even at high redshifts, galaxies aren't distributed uniformly. They show clustering, alignment along preferred directions, signs of large-scale structure already emerging. This early structure formation was expected from theory, but hadn't been observed directly before Webb. The observations confirm that gravitational instability, the process by which denser regions grow denser, was already operating efficiently in the first billion years after the Big Bang. Studying the cosmic web helps cosmologists test their models of structure, formation. The specific pattern of filaments and voids depends on the properties of dark matter, the amount of dark energy, the initial density variations from the Big Bang, and the expansion history of the universe. By measuring the web's properties at different times, through observations at different redshifts, astronomers constrain these fundamental parameters: light, time, and observation. Let's return to a fundamental point. When we observe distant objects, we're not seeing them as they are now. we're seeing them as they were when the light left them. This creates a strange situation. Consider a galaxy whose light has been traveling for 13 billion years. We see that galaxy as it appeared 13 billion years ago. But the galaxy itself has continued evolving during all that time. What does it look like now? We don't know. We can't know, not yet, because the light showing its current state hasn't reached us yet. That light is en route. It's traveling through space toward us. Tens of billions of light years from here, at the galaxy's current location, which is much farther than where we see the galaxy because space has expanded, photons are leaving at this moment. Those photons will travel for tens of billions of years through expanding space before reaching Earth. If anyone is still observing on Earth in that distant future, they'll see that galaxy as it appears now. But we today see only the past. The farther away something is, the older the light, the deeper into history we peer. This has profound implications. We cannot study a single galaxy over time by watching it evolve. The evolution happens far too slowly. No galaxy changes noticeably over human timescales, or even over timescales of thousands or millions of years. To see galaxy evolution, we must look at different galaxies at different distances, seeing them at different stages of their lives. A galaxy 1 billion light-years away shows us galaxies as they were 1 billion years ago. A galaxy 10 billion light-years away shows us galaxies as they were 10 billion years ago. By comparing these populations, we piece together an evolutionary sequence. It's like studying human development by looking at photographs of many different people at different ages. You never see the same person at multiple ages, but by comparing enough individuals, you can trace typical patterns of growth and change. The technique works because galaxies, while all unique, follow similar general patterns. Galaxies of similar mass form and evolve in broadly similar ways. By studying large samples, astronomers can identify these patterns and distinguish them from individual variations. This method has revealed how galaxies change over cosmic time. Young galaxies, seen at high redshift, are typically smaller, more irregular, forming stars rapidly, and often interacting or merging with neighbors. Older galaxies, seen at lower redshift closer to the present, are typically larger, more organized, with slower star formation rates and fewer mergers. The overall picture is one of assembly and maturation. Galaxies grow over time through star formation and mergers. They gradually build up mass, develop structure, and settle into stable configurations. Star formation rates peak relatively early, when the universe is a few billion years old, then gradually decline. By the present day, most galaxies form stars much more slowly than their ancestors did. Our Milky Way fits this pattern. It's an evolved, mature galaxy with most of its stars already formed. Star formation continues, but at a modest rate. Much of the galaxy's history involves earlier epochs we can only study by observing distant galaxies or by examining very old stars in our own neighborhood. The limits of observation and understanding. We've reached a point where we should acknowledge the limits of knowledge. Astronomy provides incredible insights into cosmic history, but significant unknowns remain. We don't know what dark matter is. We don't know what dark energy is. Together, these constitute 95% of the universe's content. We understand only the remaining 5%, the ordinary matter made of atoms. We don't fully understand how the first stars formed. We have theories, we have simulations, but we lack direct observations of the process. Finding population 3 stars or watching protostars form at high redshift would provide crucial data. but these observations remain at or beyond current capabilities. We don't know whether life exists elsewhere. The discovery of thousands of exoplanets has shown that planets are common, but we haven't yet detected definitive signs of life beyond Earth. The question of whether we're alone remains unanswered. We don't know the universe's ultimate fate with certainty. Current evidence suggests eternal expansion and eventual heat death. But this depends on properties of dark energy that we don't fully understand. The very long-term future remains speculative. We don't know if the observable universe is all that exists. The Big Bang might have created a vast or infinite expanse, of which we see only a finite portion. There might be regions forever beyond our observation, separated from us by more space than light can cross. We don't know if our universe is unique. Some theoretical frameworks suggest multiple universes might exist, each with potentially different physical laws. These ideas are highly speculative and may be untestable, pushing the boundary between physics and philosophy. These unknowns aren't failures of science, they're frontiers. Each unknown represents a question worth pursuing, a mystery inviting investigation. Science proceeds by asking questions, developing methods to answer them, and discovering new questions in the process. The history of astronomy is one of expanding horizons. Each new instrument reveals phenomena that previous generations couldn't imagine. Galileo's telescope showed Jupiter's moons and Saturn's rings. Later telescopes revealed nebulae, galaxies, the expanding universe. Radio telescopes found pulsars and quasars. X-ray and gamma-ray telescopes discovered exotic phenomena like neutron stars and black hole accretion disks. Webb represents the latest step in this progression. It sees farther and more clearly than previous instruments. It has revealed unexpected features of the early universe, and undoubtedly, it will reveal more surprises as observations continue. But Webb is not the end. Future telescopes are already planned. Larger mirrors, more sensitive detectors, new wavelength ranges, each will push the observational frontier further. Eventually, we'll reach fundamental limits. The cosmic microwave background represents one such limit. We cannot see past it because the earlier universe was opaque. The distance to the cosmic dawn represents another approaching limit. There were no stars to see before that time. But even within these limits, much remains to discover. The volume of space we can observe is vast. Most of it has never been surveyed in detail. Countless galaxies await discovery. Countless phenomena remain unobserved. The known universe is already incomprehensibly large, and most of it remains unexplored. Reflection on scale and significance. We've covered vast distances and enormous time spans. Let's take a moment to consider what these scales mean for our perspective on existence. The universe is incomprehensibly large. The observable universe alone extends tens of billions of light years in all directions. It contains trillions of galaxies. Each galaxy contains billions or trillions of stars. Many of those stars have planets. The total number of potentially habitable worlds staggers the imagination. Against this vastness, Earth is microscopically small. Our planet is one among trillions upon trillions. Our sun is one star among hundreds of billions in an ordinary galaxy. Our galaxy is one among trillions in the observable universe. This perspective can feel diminishing. In cosmic terms, humanity occupies essentially zero space, exists for essentially zero time, matters essentially not at all. The universe will continue long after we're gone, completely indifferent to our existence or absence. Yet this same perspective can be empowering. We are the universe become conscious. Matter, organized through billions of years of cosmic evolution, has reached a configuration that allows self-awareness. Atoms formed in ancient stars, through processes spanning cosmic history, have assembled into structures capable of contemplating their own origins. We are, in a very real sense, the universe observing itself. When you look at images from Webb, matter is examining matter. The elements in your eyes, formed in stellar nucleosynthesis billions of years ago, are receiving light from other stars whose fusion is creating similar elements now. You are stardust, looking at stars. This connection is not metaphorical, it's physical. The atoms comprising your body were created in stars and scattered into space by supernovae. They drifted through the galaxy for millions or billions of years. Eventually, they became part of the molecular cloud that collapsed to form our solar system. Some fell into the disk that became Earth. Through geology and biology, they ended up arranged in the pattern that is you. You are a temporary arrangement of borrowed atoms. Those atoms existed before you and will exist after you, eventually returning to the cosmos through one path or another. But for a brief time, measured in decades against the universe's billions of years, they're organized in a way that produces consciousness, thought, wonder, understanding. This is perhaps the universe's most remarkable property. Not its size, not its age, not its complexity, but its capacity to produce beings capable of comprehending it. The laws of physics, operating over cosmic time, inevitably produce complex structures. Galaxies, stars, planets, molecules, life, mind. Whether this happens commonly or rarely, we don't yet know. Life might be abundant in the universe, with countless other consciousnesses contemplating similar questions. Or life might be exceedingly rare, with Earth hosting one of the few islands of awareness in a vast ocean of lifeless matter. Either possibility is profound. If life is common, the universe is rich with perspectives, with infinite variations on the theme of existence. If life is rare, then consciousness is precious, a fragile flame that must be protected and cherished. The practice of cosmic humility. Studying the universe encourages a particular kind of humility. Not the humility of worthlessness, but the humility of perspective. When ancient humans looked at the sky, they placed themselves at the center. Earth was the center of creation, humanity the pinnacle of existence, human affairs the primary concern of cosmic forces. This perspective is natural. We experience reality from our own position. Our concerns loom large in our awareness. It's easy to assume we're significant simply because we're present. Astronomy has systematically displaced us from centrality. Earth is not the center of the solar system. The sun is. The sun is not the center of the galaxy. It's an ordinary star in an ordinary location. Our galaxy is not the center of the universe. There is no center. The universe looks approximately the same from every vantage point. This displacement, sometimes called the Copernican principle, is humbling. We're not special in location. We're not special in composition. We're made of common elements following ordinary physical laws. Our planet orbits an average star in a typical galaxy in an unremarkable region of space. Yet this humility opens space for genuine wonder. If we're not special, if the universe doesn't revolve around us, then we can appreciate it for what it actually is, rather than what we wish it to be. We can recognize beauty without needing it to be about us. We can find meaning in understanding rather than in assumed importance. The universe is not hostile to us, but neither is it designed for us. it simply is. It operates according to impersonal physical laws that produce galaxies, stars, planets, and occasionally, on at least one planet, life and mind. This is neither cruel nor kind. It's neutral. Reality without agenda. Finding ourselves in this context, briefly alive on a small world orbiting an ordinary star, we can choose our response. We can feel diminished by the scale, or we can feel connected to the whole. We can see our insignificance as negation, or we can see it as liberation from the burden of cosmic importance. Perhaps the healthiest perspective combines both. Yes, we're small. Yes, we're brief. Yes, in the grand scheme, we barely register. But also, we're here. We're conscious. We can observe, understand, appreciate. We're part of the universe's ongoing exploration of its own possibilities. The process of scientific discovery. It's worth considering how we've learned what we know about the universe. The process is gradual, collaborative, self-correcting, never complete. Science proceeds through observation, hypothesis, testing, and revision. Someone observes a phenomenon. They propose an explanation. That explanation makes predictions. Other researchers test those predictions. If predictions match observations, the explanation gains support. If predictions fail, the explanation is revised or discarded. This process has no endpoint. Every answer raises new questions. Every solved mystery reveals new ones. The frontier of knowledge expands outward, encountering ever more unknown territory. Astronomy faces particular challenges. We cannot perform controlled experiments on galaxies. We cannot manipulate stars or replicate cosmic conditions in laboratories. We can only observe. We must infer processes from distant light and indirect effects. This limitation makes astronomy dependent on instruments. Better telescopes enable better observations, which enable better understanding. The history of astronomy is largely the history of improving observational capabilities. Webb represents a significant advance in these capabilities, but it's one step in a longer journey. Previous telescopes provided the foundation of knowledge that Webb builds upon. Future telescopes will build upon Webb's discoveries, seeing farther and more clearly still. The collaborative nature of science deserves emphasis. No single person could design, build, launch, and operate a telescope like Webb. It required thousands of people across multiple continents over several decades. Engineers, scientists, technicians, administrators, all contributing their expertise. The data Webb collects is shared with the global astronomical community. Researchers worldwide analyze the observations, publish findings, debate interpretations, refine understanding. No single institution or nation owns the knowledge. It becomes part of humanity's collective understanding. This collaborative process, while sometimes slow and contentious, has proven remarkably effective at building reliable knowledge. Scientific consensus forms when multiple independent lines of evidence point to the same conclusions. That consensus can be overturned if new evidence emerges, but it takes substantial, well-verified observations to do so. The willingness to revise understanding in light of new evidence is science's great strength. Scientific knowledge is not dogma. It's our current best understanding, always subject to improvement. This provisional nature, far from being a weakness, is what allows science to progress. Light as information. Throughout this discussion, light has been central. It's worth considering what light actually is and why it matters so profoundly for astronomy. Light is electromagnetic radiation. It's a wave in the electromagnetic field, oscillating electric and magnetic components, propagating through space. Light can also be understood as particles, photons, discrete packets of energy. This wave-particle duality is fundamental to quantum physics, but for most purposes, either description works. What makes light special for astronomy is that it carries information. When a photon is emitted by a star, it carries information about that star: its temperature, composition, motion, magnetic field. If that photon survives the journey across space and enters a telescope, the information can be decoded. Different wavelengths of light carry different information. Visible light shows us stellar surfaces, glowing gas clouds, galaxy structures. Infrared reveals dust-enshrouded regions, cool objects, distant redshifted galaxies. Ultraviolet highlights hot stars and energetic processes. Radio waves reveal molecular gas, pulsars, supermassive black hole jets. X-rays and gamma rays expose extreme phenomena like neutron stars and black hole accretion. Each wavelength provides a different perspective. Observing across many wavelengths provides a more complete picture than any single wavelength could. The speed of light, while fast, is finite. This creates the light travel time effect that makes astronomy a time machine. But it also means there's a maximum rate at which information can travel. Cause and effect are separated by light travel time. Nothing can influence anything else faster than light can travel between them. This limit structures the universe in fundamental ways. Events in distant galaxies cannot affect us until light carrying information about those events arrives. We live in a present moment defined by our past light cone. All the events whose light has had time to reach us. Similarly, we can only influence regions within our future light cone. All the locations our light or signals will eventually reach. Most of the observable universe lies outside this cone. We see it, but we can never interact with it. The expansion of space carries it away, faster than light can cross the growing distance. This creates a kind of cosmic loneliness. Most of what we observe is forever unreachable. We can see other galaxies, study them, understand them, but we can never visit. They're permanently separated from us by distances too vast and growth too rapid. Yet the light carries enough information that we can know these distant places in meaningful ways. We can determine what they're made of, how they move, how old they are, what processes occur within them. Light bridges the distance, even if matter cannot. The arrow of time. We've discussed looking backward in time by observing distant objects, but there's an inherent asymmetry here that deserves attention. We can see the past, but we cannot see the future. This seems obvious, but it reflects a deep property of the universe, the arrow of time. Time flows in one direction: past, present, future. Cause precedes effect. Entropy increases. This directionality is fundamental to our experience. In physics, most fundamental laws are time-symmetric. The equations describing electromagnetism, gravity, even quantum mechanics work equally well running forward or backward in time. Yet clearly, time has a direction. Processes that happen forward don't happen in reverse. Eggs break, but don't unbreak. Stars burn, but don't unburn. Memory records the past, not the future. The arrow of time emerges from entropy, the tendency of systems to evolve toward disorder. The second law of thermodynamics states that in closed systems, entropy never decreases. This creates a preferred direction. Systems evolve from low entropy to high entropy states. The universe began in an extremely low entropy state. The early universe was remarkably smooth and ordered. All the matter and energy compressed into a small volume, but distributed nearly uniformly. This initial condition allowed structure to form as entropy increased. As time passed, tiny density variations grew into galaxies, stars, planets. Structure formed, which might seem like a decrease in entropy, but the overall entropy of the universe increased due to the waste heat generated by star formation and other processes. Localized decreases in entropy are permitted as long as they're outweighed by increases elsewhere. This arrow of time is why we can see the past, but not the future. Light from past events has had time to reach us. Light from future events hasn't been emitted yet. The causal structure of space-time, combined with the finite speed of light, creates a fundamental asymmetry. For astronomy, this means we observe history. We see the universe as it was, not as it is. We can study how galaxies formed, how stars evolved, how structures changed. We can piece together a timeline from the Big Bang to the present. But we cannot directly observe what will happen next. We can only predict, based on understanding of physical laws. These predictions are often reliable on short timescales. We can predict planetary motions centuries in advance. We can predict when stars will exhaust their fuel based on their mass and composition. We can predict that colliding galaxies will merge over hundreds of millions of years. But on very long timescales, uncertainty grows. We don't know if dark energy will remain constant or change. We don't know if protons are stable over timescales of 1040 years. We don't know what might happen in the incomprehensibly distant future. The arrow of time ensures that the future remains uncertain while the past becomes gradually more knowable as light from distant regions reaches us. Astronomy is fundamentally a historical science, reconstructing what happened rather than predicting what will happen. The beauty of the night sky. Beyond the science, beyond the data and analysis, there's something more fundamental: the simple beauty of the night sky. For most of human history, humans looked up at stars with wonder. They created stories, myths, patterns. They navigated by stars, timed their activities by celestial cycles, wondered about the nature of those distant lights. Modern astronomy has revealed what those lights are. We know they're distant suns, many with their own planets. We know the distances involved, the physics at work, the life cycles of stellar populations. This knowledge doesn't diminish wonder. If anything, it deepens it. Knowing that the light entering your eyes left a star hundreds or thousands of years ago adds meaning to the experience. Knowing that the atoms in your body were forged in stars adds resonance to the connection. Knowledge enriches rather than depletes the encounter. Yet the simple aesthetic experience remains valid. Stars are beautiful regardless of understanding. The Milky Way stretching across a dark sky inspires awe, whether you know it's our galaxy seen edge-on or not. The experience comes first. Understanding follows. In our modern world, many people rarely see true darkness. Light pollution from cities washes out the night sky. Where previous generations saw thousands of stars, modern urban dwellers see dozens. The Milky Way, once a common sight, is now unfamiliar to much of humanity. This is a loss worth acknowledging. Not just a loss of astronomical knowledge, though that matters, but a loss of connection to something fundamental in human experience. The night sky reminds us of our place in a larger cosmos. Losing that connection, we risk forgetting that we're part of something vast. Finding dark sky, where stars shine undimmed by artificial light, offers a profound experience. The sheer number of visible stars overwhelms. The depth of the sky becomes apparent. On the darkest nights, the Milky Way casts shadows. Meteors streak overhead. Satellites glide past. The sky reveals itself as busy and alive rather than static and empty. This experience connects us to our ancestors, who saw the same sky we do. The constellations they named are the same ones we see. The planets they watched are the ones we watch. The moon that governed their nights is our moon. Across thousands of years and countless generations, the sky provides continuity. Yet we see it with knowledge they lacked. We know what stars are, how they work, how far away they lie. We know the planets are worlds, some perhaps harboring life. We know the fuzzy patches that puzzled ancient astronomers are distant galaxies, island universes beyond our own. This combination, direct experience plus understanding, provides the fullest appreciation. The sky is beautiful to look at and meaningful to understand. Both aspects matter. Webb's legacy. The James Webb Space Telescope will operate for many years. Its instruments will continue gathering light from the distant universe. Data will accumulate. Discoveries will follow. Eventually, Webb's mission will end. Its fuel will run out, or its instruments will degrade beyond repair. It will join previous telescopes in retirement, its contribution complete. But the knowledge it provided will remain. The images will persist. The data will be available for future researchers to analyze and reanalyze. Discoveries yet unmade hide in existing observations, waiting for someone to notice them. This is how science builds. Each generation of instruments provides data that outlasts the instruments themselves. Future astronomers will study Webb's observations, finding patterns that current researchers miss, asking questions we haven't thought to ask. Webb's most important legacy might not be its specific discoveries, but rather the questions it raised. By pushing observations to earlier cosmic times, it revealed how much we don't understand about galaxy formation, black hole growth, early star formation. These unknowns motivate future research. In this sense, every scientific instrument is most valuable for revealing what we don't know. The known is comfortable. The unknown is where progress happens. Webb has expanded the boundary of knowledge, revealing vast territories beyond that remain unexplored. Future telescopes will explore those territories. Plans already exist for larger mirrors, more sensitive detectors, longer observation times. Each will see what Webb cannot, extending the observational frontier further still. But there are limits. Eventually, we'll reach the cosmic dawn itself, the moment when the first stars ignited. Before that, there's nothing to see. No stars, no galaxies, just dark ages. We might reach other limits too. The faintest objects possible to detect. The most distant objects whose light hasn't been lost to expansion. The point where gravitational lensing can no longer help because there are no background objects to magnify. These limits, rather than representing endpoints, frame the territory of knowledge. Within these limits lies everything we can potentially learn through direct observation. That's a vast space, mostly unexplored. Enough to occupy astronomers for generations or centuries. Beyond these limits lie things we might understand through theory and inference but never directly observe. The earliest moments after the Big Bang. The interior of black holes. Other universes, if they exist. Regions of space beyond the cosmic horizon. Some questions might remain permanently unanswerable, not because of practical limitations, but because of fundamental ones. This is acceptable. Not everything needs to be known. Mystery has value. The universe doesn't exist to be understood. Understanding is something we pursue because we're capable of it and drawn to it. But the universe's indifference to our knowledge is not a failing. Conclusion. Looking forward, As we conclude this journey through cosmic space and time, what remains to be said? The universe is vast, far larger than human imagination can comfortably hold. It's ancient, existing for nearly 14 billion years before most of it could possibly notice its own existence. It operates according to physical laws that we've partially deciphered but don't fully understand. Within this universe, on one small planet orbiting an ordinary star, matter has organized itself into forms capable of observation, thought, wonder, and understanding. We are those forms. Brief, fragile, limited, yet capable of comprehending our own context. This comprehension is recent. For most of human existence, our understanding of the universe was limited to what could be seen with naked eyes. Only in the last few centuries have instruments extended our vision. Only in the last century have we understood the universe's basic structure. Expanding space, billions of galaxies, history beginning with the Big Bang. The James Webb Space Telescope represents the latest advance in this expanding understanding. It has shown us galaxies from cosmic dawn, revealed black holes that shouldn't exist, found structures that challenge our models, raised questions that will occupy researchers for years. But Webb is a tool, not an endpoint. It's one step in an ongoing process of discovery. Future instruments will surpass it, as it surpassed Hubble, as Hubble surpassed earlier telescopes. Each generation sees farther and more clearly than the previous one. This progression will continue as long as humans retain the capacity and desire to observe the cosmos. We are driven by curiosity, by a desire to understand our place in existence. This drive is fundamental to human nature. As long as we exist, we'll keep looking outward, asking questions, seeking answers. What we find will sometimes confirm our expectations and sometimes surprise us. The universe is under no obligation to make sense to us. But it does make sense, at least partially. The fact that we can understand even a fraction of cosmic reality is remarkable. We inhabit a universe that allows understanding. Physical laws are consistent, knowable, expressible in mathematics. Observations made here apply to distant galaxies. The same elements, the same forces, the same processes operate everywhere we can see. This universality makes astronomy possible. If physical laws varied from place to place or time to time, if the universe were fundamentally chaotic or arbitrary, understanding would be impossible. But it's not. Order underlies the apparent chaos. Patterns emerge, predictions work. The universe, despite its vastness and complexity, is comprehensible. This might be the most remarkable fact of all. Not that the universe exists, but that it exists in a form that permits beings within it to understand it. We are the universe understanding itself. Matter contemplating matter. Existence aware of existence. In quiet moments, looking at images from Webb or the night sky itself, this realization can feel overwhelming. You, a temporary arrangement of atoms, are connected to all of this. Your awareness, brief as it is, participates in something vast and ancient. The light reaching your eyes has traveled for billions of years. The atoms comprising your body were forged in stars that died before Earth existed. The physical laws governing your existence are the same laws that govern distant galaxies. You're not separate from the cosmos. You're an integral part of it. This perspective offers no answers to personal questions about meaning or purpose. The universe doesn't provide those, but it offers context, a framework for understanding our place. We're small, yes. Brief, yes. But we're here. We're aware. We can observe and understand. That's enough. It has to be. The universe offers nothing more, But it also requires nothing more. Simply being here, briefly conscious in an ancient cosmos, participating however briefly in the ongoing exploration of existence. This is the situation we find ourselves in. How we respond is up to us. We can choose curiosity over indifference, understanding over ignorance, connection over isolation, wonder over cynicism. The universe doesn't care which we choose, but we're not doing this for the universe. We're doing it for ourselves, because we're the kind of beings who can wonder and understand and who find meaning in doing so. The James Webb Space Telescope looks outward into space and backward into time. It sees galaxies forming, stars igniting, structures assembling. It sees the universe as it was, young and raw and actively creating itself. We look at those images and see our own origins. We see where we came from, the cosmic processes that eventually led to planets and life and minds. We see ourselves reflected in the ancient light of distant stars, and in seeing, we participate in one of the universe's possibilities, awareness of itself. For a brief moment, in one small location, the cosmos notices its own existence. That noticing is what we offer. Our brief awareness, our limited understanding, our small perspective on incomprehensible vastness. It's not much, measured against the scale of the universe, but it's what we have, and it's enough. The universe continues its expansion into the future. Stars will continue forming for billions of years. Galaxies will continue evolving. Eventually, trillions of years hence, everything will fade. The stars will go dark. The universe will grow cold and empty. But that's inconceivably far ahead. For now, for our time, the universe is young and bright and full of possibilities. Stars shine, galaxies swirl, structure fills the cosmos. And here, on one small world, beings briefly exist who can observe it all and wonder. That's where we are. That's what we found. That's what telescopes like Webb help us see. The vast, ancient, beautiful cosmos that gave rise to us and that we, for a little while, can comprehend. The journey continues. New observations await. New questions will arise. Understanding will deepen and expand. But for now, this is enough. To know that we're part of something vast. To understand, even partly, where we came from and where we're going. To look at the stars and recognize them as kin. The universe is our home, all of it. Every star we see, every galaxy Webb reveals, every atom in existence. It's all connected, all part of the same cosmic story. And we're part of that story. Brief participants, yes. Small, yes. But participants nonetheless. That participation, that awareness, that understanding, this is what makes us human. This is what drives us to build telescopes and study distant light and piece together the history of everything. We do it because we can, because we're the kind of beings who wonder. And in wondering, we fulfill something fundamental in our nature. The universe gave rise to matter capable of understanding. We are that matter. And as long as we exist, we'll keep looking up, keep asking questions, keep seeking to understand the vast and ancient cosmos that made us possible. That's our nature. That's our gift. That's what we offer to existence. Awareness, however brief, of itself. And perhaps that's enough.